We have learned that when two charges, either similar or dissimilar in nature, are brought closer, they apply a force on each other. But have you ever wondered what is the quantity of electric force between the charges in an interaction? Charles-Augustin de Coulomb, a French military engineer and physicist, established a relation to find this quantity of charge. This statement given by him, called the Coulomb's law, is a quantitative statement about the force between 2-point charges. But first, it is important to understand what point charges are. When the linear size of charged bodies are much smaller than the distance separating them, the size may be ignored and charged bodies are treated as point charges. Now, coming back to the force between the charges, Coulomb measured the force between 2-point charges. He made two conclusions. First, the force between the charges varied inversely as the square of the distance between the charges, and second, the force between them was directly proportional to the product of the magnitude of the two charges and acted along the line joining the two charges. Mathematically, if we have 2-point charges, say Q1 and Q2, in vacuum separated by distance r, then the electric force F between them is given as F is directly proportional to Q1 Q2 over r squared. The proportionality sign is replaced with Coulomb's constant denoted by K. So the relation becomes F is equal to K Q1 Q2 over r squared. Conventionally, the value of K is given as 1 upon 4 pi epsilon naught, and numerically it is approximately equal to 9 into 10 raised to the power of 9 Newton meter squared over Coulomb squared. The epsilon naught represents permittivity of free space, and its numerical value is 8.854 into 10 raised to the power of minus 112 Coulomb squared over Newton meter squared. But did you know how did Coulomb come to this law from his experiments? He measured the force between two charged metallic spheres using a torsion balance which he invented himself. There is a needle freely suspended using a fiber inside a glass chamber. On one end of the needle, a small brass disc is fixed, and on the other end, a sphere of greater width is fixed. A scale is subscribed on the outer chamber to measure the torsion produced in the fiber. As the charges on the sphere were initially unknown, so Coulomb thought of a simple way. Suppose the charge on a metallic sphere is Q. He put the sphere in contact with an identical uncharged sphere. Due to symmetry, both the spheres acquired a charge of magnitude Q by 2. He repeated the process and the charge is distributed every time as Q by 2, Q by 4, etc. Similarly, he varied the distance for a fixed pair of charges. Finally, he compared the forces for different pairs of charges at different distances. As a result, he concluded the Coulomb's law as shown. In the honor of Coulomb, the SI unit of charge is named as Coulomb. Putting this value of K and charges separated at a distance of 1 meter, the force acting between the two charges comes out to be 9 into 10 raised to the power of 9 newtons. So we can say that 1 Coulomb is the charge that when placed at a distance of 1 meter from another charge of the same magnitude in vacuum experiences an electrical force of repulsion of magnitude 9 into 10 raised to the power of 9 newtons. 1 Coulomb is a very big unit of charge, and we do not find it useful in practical application. So in electrostatistics, smaller units like 1 millicoulomb for 1 microcoulomb. Thank you for watching this video.